Okay, here we are. So, a warm welcome to the editors and to the auditorium for this expert talk, the first in 2022, handled from my desk in my office in the nice village of Laboe at the Baltic Sea, where in summertime I just can walk over to the beach. So there are plenty options what to do in addition to the work. So we will start with I think we have a number of editors here. It's Christian Felgemacher from ROHM Semiconductor, Klaus Grambichler from Infineon Technologies, Benjamin Sahan from the University of Hannover in Germany. And we have people from NoMIS Power, and I have 4 on the list. I'm not quite sure if they all are already here. I have Anant,
Woogje-san.
I have Adam Morgan. I have Woogje Song und Gehan and Amaratunga. So I hope I haven't spelled it nearly right, but important is the technical content we are now starting to discuss. So we will get from our backstage the questions from the people from the field, and we will momentarily start with the questions. It's addressed to NoMIS Power. What's the mission of NoMIS Power, and why did you and the other founders start the company? And what do you hope to achieve? Very interesting questions to find out.
Yeah, I can handle this, Bodo.
Adam, go ahead.
So I know we're new here to the scene. We've attended on the other end, but not on the talking panel. And so myself and colleagues just want to say a welcome hello and thank you so much for having us. But as we've seen, there's been a lot of growth in the electrification and digitization of our world, and with the availability now of foundries in the silicon carbide space, just like with the silicon space, it now opens up the market to new entrants in a fabless model such as ours, where we're able to basically bring together our decades of combined experience, both in the silicon carbide device, but also the silicon carbide packaging expertise to bring not only our own internal innovative devices and designs to the forefront, but also to help other new entrants as well entering into the silicon carbide market and technology space avoid certain hurdles when trying to get into bringing in silicon carbide into maybe their own technology roadmaps. And so we've just felt that there's a need in the market for our our knowledge and our background, and also we see a large opportunity here for us to bring our innovations as well from the device through the packaging to try to compete in some of these new niche areas that'll have opportunities.
Thank you, Adam. Any more comments from the colleagues? So we will move to the next question, which is addressed to ROHM. what are the key benefits of the new generation of SiC MOSFETs soon to be launched by ROHM?
Yeah, thank you. So first of all, also thanks from my side for being included in this event today. So to come to the question, basically the fourth generation of our SiC MOSFETs, which we are about to release to the market in the next weeks, and will follow up with multiple announcements probably in this quarter. I will just concentrate on three aspects maybe that are key benefits of these devices. The first one is, of course, that for the same chip area, we can reduce the RDS on by approximately 40% over our previous product. And of course, that gives the benefit that you need less chip area for either the same performance, or you can have more performance for the chip area depending on what you're desiring. And ultimately, that of course can have certain cost advantages for the system perspective. But not only on the static performance or RDS on characteristics, our device significantly improved. We also have improved the dynamic behavior significantly. So the turn on and turn off losses have further reduced compared to the previous device. And both of these improvements we have achieved while maintaining robustness. So we did not sacrifice short circuit withstand capabilities, for example, for RDS on improvement. We still have a device that is very robust. And also due to the improvement of capacitance ratios, the usability has increased. So there is less effect due to high DVDT on the gate voltages, for example, which sometimes can be challenging in building driver circuits around a very fast switching SiC MOSFET. So I would say these three aspects are probably the key benefits. There are others, but I think this is what we should focus on for now.
Thank you, Christian. Let me ask one question. You mentioned reducing of die size. My memory has that every time while I was doing application and marketing at Harris, when we reduced in silicon dies the die size, the thermal behavior to the reduced die size made a big impact that we had with the bigger die, a better thermal behavior. Is this under certain control that there are no surprises for the user?
Certainly. I mean, you are completely right. The smaller the die gets, the more difficult it is to extract the heat generated. Even of course, if the RDS1 is better, some of this improvement cannot be exploited because you still have to maintain the chip temperature. So you're fully right in that the reduction of such chip size does play a role as well. So it doesn't necessarily mean that you can have a 40% smaller device, but the truth will be still somewhere in between what you gain in improved RDS1. You partially have to, of course, account for in terms of a slightly increased thermal resistance, all other things being equal. So you can, for example, to pass the same DC current, you cannot make the die 40% smaller, but you can still make it smaller and reduce the size.
Okay, Christian, thank you. And we are ready for the next question. So the question is to Infineon and to the Hannover University. Why does the low parasitic inductance of a current sensor support the wide bandgap designs?
Yes, thank you for the question, and thank you also for being here in this event. My name is Klaus Grambichler, working for Infineon. I'm responsible for the current sensor, which was chosen for these trials to protect this silicon carbide power bridge. And the unique feature of our current sensor is a package that has a current rail going through the lead frame, but it's it's also done by the competition. But what is unique in our package is that it's an SMD solder pad that is very nice connected to the PCB, and just for 0.1 millimeter we are inside the package, and then we are already out again. So if you have this strip design for, rules in the PCB, following a ground plane, and you have the PCB traces on top, and you put our device there, you are almost always on the same distance to the ground plane. So it's really an RF design which is applied here on our lead frame, and for this reason we managed to put here a parasitic inductance of less than 1 nanohenry from one edge of the package to the other edge of the package, following these rules of microstrip design. And this is a really outstanding number where no chance and nothing can be that easy there. And we are there. And so if this current sensor is put into the power loop of your silicon carbide bridge, we will almost not add any parasitic inductance because of less than 1 nanohenry. Basically, this is the answer.
Thank you. That sounds great.
It's great.
It is, yes. Thank you, Klaus. Klaus, where you are located?
We are located in Austria, in Villach.
Okay.
Where Infineon has some part of its headquarters in the power semiconductors, as you probably know.
I visited Villach a while ago.
Okay.
We had a bus ride from Munich together with Reinhard Ploss.
Oh, this is nice.
That was more than 10 years ago, roughly.
Yeah. Now he retired recently. You probably noticed it.
I noticed that, and I should retire also, but I still have so much fun. I'm 68, and I like to run my magazine, but a little bit more in the background. The youngsters do more and more everything, and I'm only here to do the talks. Okay, we are ready for the next question. It's to NoMIS. As a new commercial entrant into the SiC space, how are you addressing the challenges in developing a SiC supply chain? Who wants to answer?
Anant, you are muted.
Oh yeah.
Hi, this is Anant Agarwal from NoMIS. I will try to answer this question, and maybe part of it can be answered by Gehan. The supply chain issue is really tricky for companies like us that are fabless. Obviously, we have XFab in US, we have Classic in Scotland. We have several new foundries coming on in Asia, which we plan to use. So right now we are engaged with all the possible foundries and looking for the best way to proceed here. Gehan, can you add something?
Thank you, Anant, and thank you, Bodo, for the introduction. As Anant mentioned, as a fabless player entering into the silicon carbide space, we see our key capabilities in the area of design, but also in development of new processes with players, including foundries around the world. And what we're doing innovatively at NoMIS is not only having colleagues like our colleague, Professor Woogje Singh, working on new innovative designs for silicon carbide, but we're also working very closely with different foundries around the world to develop the kind of processes that will help our clients and customers implement new silicon carbide technologies in different locations. So I think that integrated approach, working with multiple foundries in different locations and different geographies, and having a really collaborative approach with our clients is very key to building a sustainable silicon carbide supply chain.
We're ready to receive the next question. A question to Rome. Can you tell us anything else about the markets you're addressing with the new SiC MOSFET generation?
Yes, I will try to answer that as much as I can. So basically, we do believe that for SiC, one of the key markets will be the automotive sector. So we are very strongly addressing electric vehicles with our SiC portfolio that is going to come up. So we will be offering chips to go into electric vehicles of the upcoming voltage classes for battery systems, both for the main drive inverter, but also for additional systems in the EVs, such as onboard charging units and also aspects such as DC-DC converters in EVs. But automotive is not the only area we are addressing. We are also addressing a various number of industrial applications. One key area, of course, is the renewable energy sector. We see more and more renewable energy systems, fortunately, being added to the energy mix. So we also see very strong opportunities in PV, for example, but also other sources of renewable energy. And finally, also the interface between the automotive and industrial world, where we, for example, see applications on the industrial side, which have to do with high-speed charging of electric vehicles and potentially in the future also larger charging systems for other vehicle classes, I could imagine. So with a new fourth generation, we are addressing all these markets. The devices will come out in discrete packages for systems of smaller sizes, like onboard chargers, smaller inverters for industrial applications. But we will also be offering chips and addressing module applications for traction inverters, for example, in electric vehicles.
Thank you, Christian. The question to Infineon again, what's the typical application for the SiC product? I mean, for this particular SiC MOSFET shown in the paper.
Thank you for the question. Maybe Benjamin, do you have here a proper answer?
Yes, I think we can say that it's a six-pack, a two-level six-pack half-bridge. So a typical application here would be the industrial drives application, where you power a frequency converter with. And this is also, we have addressed here in the paper that we limit the DVDT to typical slope of 5 volt per nanosecond, and this is very common in industrial applications. So we actually have to slow down the MOSFET a little bit, but still we get a superior performance. I think this is widely known, but in industrial applications you need short circuit robustness and short circuit protection, which is mandatory. And not all SiC MOSFET devices have this feature, but the Infineon device was designed for this application, so it can be used also for this applications, but for other applications as well, of course.
Thank you, Benjamin. A long question to Rome. I am designing a totem pole PFC using SiC MOSFETs from Rome, namely the SCT 3060 AL. In the fast switching totem pole leg, which switches at 65 kilohertz, in my application is a negative turn off recommended, since we are switching at high frequency and ringing at the gate might occur, which might create false turn on. Datasheet recommends zero voltage turn off, but many totem pole applications use negative turn off for that totem pole leg.
Yeah, thank you. Very interesting question. So first of all, maybe for the rest of the participants, the quick explanation of the device in question here. So the SCT3060AL, this is our third generation SiC MOSFET. Of course, a bit different to our fourth generation, but I will try to answer as generic as possible. So in general, of course, we do recommend, as you've mentioned from our data sheet, to turn these devices off with 0 volt. And it's always hard to give an exact recommendation for a particular converter design without knowing the particular details of the gate driving circuit, etc. However, what I can say is that the recommendation for 0 volt stands, because we also have to ensure that the gate is protected against negative gate voltage transients. And at the same time, we are confident that with 0 volt turn off, provided that you have a good gate drive design, and also that you maybe are even using a feature like Miller clamping to ensure that while the MOSFET is turned off, there's a low impedance path between gate and source. And we are confident that if such design measures are implemented, the 0 volt turn off can be very successful. What I can say, of course, is that our teams in terms of FAE and AE support are there to help you with any remaining issues or concerns that you might be having in such a situation. And that is, of course, always a case-by-case discussion. But in general, we recommend 0 volt turn off. Also, this will be similar for the new generation that is to come. We will recommend to turn this off at 0 volt. And provided that certain conditions are met in the design of the converter and the gate driver, etc., we are also very confident. You may have seen in the article also a picture of a totem pole PFC EVK that we are currently developing with a team here in Germany. And also I can say that this converter will also be using 0 volt turn off for the high frequency leg. However, here we are using the device from the fourth generation, also in a discrete package, much similar to the 3060AL, basically the direct replacement for the fourth generation.
Thank you, Christian. It will be a great thing if there is detailed need of explanation that the people who questioned it may get in direct contact with your application lab.
Of course, yes. This is always a possibility, and I would encourage everyone for particular design-related questions to contact the team. Thank you.
Thank you, Christian, and we are ready for the next. The next question is to NoMIS. For a SiFab to be converted into a SiC fab, what pieces of equipment and processes must be replaced and or added? And as SiC technology progresses, do you foresee fab conversion becoming easier, cheaper as existing processes mature and new techniques to fabricate SiC devices, SiC device architectures emerge? I think that's a good question, but the foundries may get the exact answers, but
Bodo, I can try to answer it. This is Anant Agarwal. I have some experience in this area because we worked with XFAB in the early days. So there are about 10 pieces of equipment you want to buy for silicon carbide, but the most important ones are the implanter and the high temperature annealer. And then you have to hook up the gate oxide furnace with nitric oxide anneal. And then you need a backside sputtering because most of the silicon fabs don't have a backside process. and you need a backside thinning and laser anneal process because we need to thin the wafers. And there are a few other equipments. We are extremely, as at NoMIS, are experienced in this because we worked with XFAB in the early stages, and I was the one who founded Power America to do this kind of work in US. It takes about, if it's a 6-inch silicon line, it takes about $15 million to do this. And it's really quick. There are a number of vendors already in this field, so one can easily do this. I would also add to a previous question that the strength of NoMIS is in two ways. One is cutting the development time and taking a new entrant to a qualified product within a year. And that will save a lot of time for the new entrant because we have experienced qualifications before. And number two, we have much better performance working with foundries. For example, Dr. Woogje Sung just demonstrated that we can get 10 microsecond short circuit time without compromising the performance. And as we know today, the biggest problem is we have a 2 microsecond short circuit time. And we overcome that with some interesting designs working with foundries. And I think we will add a lot of value to the new companies coming into this technology area. Thank you.
Thank you, Anant. 10 microsecond is quite a good rate to detect and take action if there is a short circuit. That's what I remember in the past for silicon IGBTs. It was sometimes in the 4-5 microsecond time. So
right. That is the biggest problem today because most vendors have only 2 to 3 microseconds.
Oh yeah, that's critical. Okay, we can go to the next question. So a question addressed to all of you. What's the cost perspective per kilowatt for automotive applications? The power can go to 200 to 300 kilowatt or higher for commercial vehicles. The question is if you can answer from the from your viewpoint.
Maybe I can only give a very high-level answer to this topic, maybe.
Thank you, Christian.
It is difficult to give euros per kilowatt comparisons, of course, for inverters or for whole powertrains, comparing between the IGBT and also SiC MOSFET world, because it depends on more than the chip. And of course, we as a chip manufacturer, we have very good information about the chip, but I wouldn't hesitate a guess for system cost. However, certain trends, of course, can be described. One important trend is that cost reduction has been happening and is happening for SiC MOSFETs per amp if you want. So if you call the price per ampere, of course, there's been significant improvement in the past. And also we have to consider on system level that whereas the SiC MOSFET per ampere or per chip area may be slightly more costly than an IGBT, there are also benefits that directly translate into cost savings elsewhere. For example, if you increase the powertrain efficiency in certain operating points, in particular in operating points where the vehicle is operating for significant periods of time in the partial load region, for example, where SiC MOSFETs are really good because they have low forward voltage drop under low current compared to IGBTs especially, and also, of course, low switching loss. And if you do that, then you can maybe save on battery costs, for example. If you want to have a certain range for a vehicle, you need certain amount of battery, and the more efficient your powertrain becomes, of course, then you can slightly reduce your battery capacity, and that also translates to cost. So what I want to say really is that this is a system level question. I think some of the system level integrators out there and OEMs, they could probably give a more detailed answer. The question is also how detailed they could, of course, be in such a forum. Yeah, that's probably all I can say to this topic.
Yeah, and I can maybe chime in and second what Christian said here as well. I mean, with the continued advancements and fleshing out of the different architectures for the converters, I think it's becoming very clear that people are seeing, several percentages, even up to as high as 10% of conversion efficiency gains per stage and the converter, and so therefore, you're clearly going to get the benefit of switching to SiC, probably first and foremost when it comes to the battery costs. And if you're talking about a 200 to 300 kilowatt converter, this is probably starting to push a little more into the medium duty and heavy duty vehicles, where I think that system level trade-off is going to have to be definitely fleshed out. But then also, if you take it to the next system level up, is thinking about as the charging infrastructure increases, perhaps you can put a hard stop on how big your battery needs to be, and thus maybe focus more on your device efficiency for a smaller battery, if you know that your vehicles can make it from point A to point B between charging locations. So I definitely think it's a very involved question that will involve much more kind of fleshing out of the understanding as the technology continues to make its way into the field, and people kind of understand these various trade-offs across all metrics.
Yeah, I fully agree with what you just said. Also, if you want to take it even further and factor in the energy cost over the lifetime of a vehicle and all the conversion efficiency stages, and at least here in Europe, we do see electricity prices being very significant now. Let's say, then of course the question changes with all these variables constantly changing. I think it's a very interesting topic, but also very difficult to give a tangible answer to. Yeah,
absolutely.
Okay, thank you, gentlemen. We are open for the next. Again, to all of you, do you see in future fabrication of SiC MOSFETs with lower internal gate resistance below 1 ohm?
Yeah, maybe I can comment. Question is what do you want to reach with this? I mean, it depends, of course, on how large your chip is, but also what you want to achieve with it. You also need a certain controllability. You can, of course, add external gate resistance, but I do believe this topic of what is the ideal internal gate resistance for a chip, letting all design constraints aside for a moment, I believe this also comes down to how you want to use this chip. Do you want to parallel a significant amount of chips, or are you looking at an application with one single chip where certain other aspects of paralleling are not so relevant? So while I do think that an RG in the range of 1 ohm or lower is on a technical level feasible, the question is whether that would yield the ideal device or not. So I do think this will always be a case-by-case topic and what you're addressing with a specific chip.
Okay, Christian. I think the 1 ohm is also a kind of insurance for stability in design, that you did not get unexpected ringing, and you are still in a good operating frequency.
Of course, okay, trade-offs like this play a major role.
Yeah, we're looking for the next question. Oh, it's a bandworm question. I will read it slowly and correct. Following to the question to NoMIS about the supply chain, in the realistic condition, it's very hard to persuade foundries to take small orders from mid-size company. Don't even say newly startup companies. I believe the person whom asked the question was meant, how could you start a real talk to busy foundries? Oh, that's always the problem, even in the past. I remember when ASICs had been introduced into automotive and into industrial, I learned that industrial volume is always too small, and automotive volume is always high to support it. That was something at Harris, I remember. So optimized gate driver from the ASIC design did not got designed because automotive had priority. But that's life, small volume.
Yeah, I think the it's certainly one of those kind of chicken and egg problems that we're as a new entrant, of course, slowly working on ourselves. But what we found to be highly successful is that having the foundries recognize that it is a mutual relationship, and as especially more of these silicon carbide foundries come online, their whole business model is about maintaining capacity and having as many wafers as they can running through the fab, throughout their existence. And so we've had success in approaching foundries by letting them know that we do have a roadmap with financial backing, which of course is necessary to fill a X percentage within their production line. And so when the managers of these fabs see that they can indeed lock in a certain amount of production that we're able to fulfill, and as well as hopefully new entrants as well, that it then starts to show in a more positive light that in fact not so much stalwart companies can have a go in this space. And so we're already looking at the initial qualifications of certain products. So that whole qualification process in and of itself, as we know, is lengthy, and therefore secures X amount of runs through the fab, as well as initial production lines at and even at relatively low volumes, maybe compared to ROHM or Infineon, it's still certainly enough to to warrant a discussion and to maintain these types of business relationships with these foundries. And I think as more of the foundries do kind of either make these conversions, as Anant mentioned, or start from the ground up, that similarly kind of like what we saw in the silicon space, there's going to be more ability to fill at these kind of smaller percentages, but with more players, the fabs are still able to to make their bottom line and to allow the relatively smaller, newer people to have a case to make within their production line. So that's a successful route that we've been able to capitalize so far on, and hopefully others can do the same.
May I add something, Bodo?
Yeah, go ahead.
I think the key here is that any new entrant, whether small size or mid size, uses the PDK offered by the foundry. So the foundry does not have to change anything for the new customer. And the innovations in design will really add the performance for a new entrant. So my suggestion is we stay with design innovations and use the fixed process offered by the foundry. And that way foundry can scale up to 1,000 customers if it needs to. And the same thing is largely happening in the silicon world. people just don't run thousands of PDKs. They would run 1 or 2 or 3 PDKs for many customers.
Okay. So general being in standard is the right. So the question to Infineon, what bandwidth of a current sensor is needed in the OBC onboard charger of an electro vehicle using SiC design?
Yes, this is a good question, and it depends where is the current sensor positioned. So at the moment, we do see 3 positions. One is the connection at the grid, where we do the power factor correction, the PFC, and there we probably have to maintain the 150 kilohertz border, and so we also see 200 kilohertz sensor bandwidth sufficient. But where it's really getting interesting is then the DC-DC converter part, where the rectified DC voltage is then transformed to the battery voltage. It has to be adapted, and there you can then fully play the silicon carbide power stage, the more high frequency. And here we see a minimum bandwidth of 1 megahertz to support here a proper regulation, sensing and regulation of this DC-DC stage. It shall be small, efficient, lightweight, so you have to go for the SiC power stage, and then you have to go for a little higher frequency and a very accurate sensing to have a good control loop in your system. So 1 megahertz minimum.
Okay, thank you. What question to all? Which are the known negative effects on the electric motor when we control it with a SiC MOSFET-based inverter? How they can be overcome?
And maybe I can comment on it. I think
Okay.
it's a fair question, but you have to consider that, of course, if you apply the intrinsic switching speed of the SiC MOSFETs, it's a unipolar device and it's very fast. And this is the main reason for a much higher efficiency. If you would use the intrinsic gate resistance or the minimal gate resistance in the data sheet, then you would end up with switching slopes of maybe 30 to 50 kilovolt per microsecond. And in fact, this is the typical electric motor is not, the isolation system is not designed for such high switching speeds. It would probably, you would see partial discharge in 10 minutes or it will burn in a very short time. So you have to slow down the device unless you use external filters, which are quite expensive and bulky. So it's, I would say, in most applications better to slow down the device. And then, of course, you can slow it down to a typical IGBT switching speed, and you can have a direct application or direct, you can have more or less the same behavior in terms of the motor than with traditional designs. But then the question still remains, what is the benefit of using silicon carbide? Well, it's mainly you have no, more or less no reverse recovery effect, and you have no, also the current slope is much faster, so you still have a significant gain in switching speed and so on. So the other question would be, if you use a little bit faster switching speed, maybe twice as high as IGBTs, how can you overcome or how can you prevent damaging the motor? There are different possibilities. For instance, you could bring the power device much closer to the motor with a integrated design. This is quite common in automotive applications. So here in integrated designs where you don't have a long cable in between, you can use higher switching speeds, and finally you can get more out of the device, let's say.
Again, to everybody of you, does any firm sell Antiserious configurations of SiC MOSFETs as a module for solid-state circuit breaker applications? Or do companies specifically design such modules for customer?
Maybe I from the sensors can give you an indication.
Yeah.
We see this trend and on the market to replace fuses by smart fuses, and we are doing some prototype modules already in the lab. So Infineon will come up soon with such modules. But as far as I know today, but I'm just a sensing guy, so I'm collaborating with my colleagues in the power labs, and then they do these anti-serious connections, and they use one of these sensors together with a microcontroller, so they can very precisely put the fusing behavior in the microcontroller, and then they switch off the circuit with this anti-serious connection. So will come soon, if not there already.
Okay, we have to look what will happen, but it's always a difficult task to use the semiconductor as a safe fusing element. It must be always guaranteed that the safe operating area is not overtaken or out of that. So would be nice to see what applications will come at that point, or if there is still some kind of fuse in series to recover the worst case situation.
Yeah, and I can add a little bit to that as well, if there's time.
Go ahead.
Thank you. So I know in some of my circles that I've come across in R&D groups, it still has been, even within some of the major power management product players, a custom kind of task for internal development of their products. As you know, there's a lot actually involved in the design of a solid state form of circuit breaker in order to kind of match the necessary redundancy and reliability of of your more conventional type. And so, looking at and understanding and trying to draw analogies of the common I squared T curve that is common to fuses and things, and kind of understanding what sort of both electrical but electrothermal performance you can get out of a module with the different packaging stack that adds thermal capacitance and can absorb the energy in these different circuit break events. And there's been many solicitations out and from government, but also internal focuses where the evaluation of, again, different topologies, whether it's anti-series or combining different power transistors and diodes together to get you the necessary switching action. I still think is something that's slowly coming to the forefront as well. So as far as my knowledge, it's probably definitely more heavy in the custom space as opposed to the a one-size-fits-all solution that we're starting to see hit the market. But again, time will tell as silicon carbide continues to improve, especially also in reliability, from the various aspects. So for example, I mean, even internally within NoMIS, we've seen advantages by shifting to different architectures and improving the gate oxides and things like that within the silicon carbide devices that we're developing that would help these types of things. So I think, again, as the technology develops, it'll open many more doors for kind of standardized products to come out.
Thank you, Adam. We're looking forward to these kind of products and what they will do good for the wide market. With the SiC, the switching is sharper, but the reverse recovery nearly disappear. So does the use of SiC increases or decreases the EMI problems? Anybody a good answer to that question?
Maybe not a direct answer, but maybe I can
Christian,
just comment a bit on this topic.
Yeah.
Of course, thank you for this answer. I believe it's difficult to answer directly in either direction, because of course the person asking is completely right that the slopes are faster potentially when using SiC, so the transient or the spectrum of transients generated is very large, but in principle, the good thing is that SiC MOSFETs tend to have very good controllability. So we've already talked about this for motor drive applications, but of course, it's also true for other applications. The VDT for SiC MOSFETs can be controlled, and also that the turn-on behavior of the MOSFET, which indirectly impacts the reverse recovery behavior of the body diode. These things tend to be controllable through gate resistors, and in general, what is of course essential for these fast switching designs, and I think that's true for any wide bandgap device design, is that the design around the power semiconductor is key. So whether it's a module, it needs to be designed to be low inductive, but also to ensure that symmetry exists, that you contain the common mode inside a defined area. And also the same is true, of course, if you design with discrete devices. It is very important to bring both the electrical design for EMI, but also for switching performance, and the thermal design into some kind of a good compromise between all the trade-offs that you have to make in the design. And I believe then EMI is manageable, as with other switching technologies as well.
Thank you, Christian. We are at the point. The last question is arriving, and then we are coming to an end with the SiC session. What are the best tools for simulation of SiC MOSFETs based power systems? SPICE, system level tools, etc. How much more development is required in this area? It's addressed to all based on simulation tools. What's your experience and what would you recommend? Gentlemen, if this is a question for the future, we will keep it. And
I can quickly maybe answer real quick.
Okay, go ahead.
I think, it might kind of depend on what exactly it is the user might be trying to capture or extract from that simulation system. But, in our experience, we've found that, accurate models of both the device and the module and package, extracting the parasitics and surrounding the necessary level 3 or level 4 SPICE model of the, maybe you could say, silicon carbide MOSFET, adds a lot of clarity to the dynamic performance of the system, electrically and switching. So that's definitely something that can be easily incorporated into SPICE and covers the entire kind of electrophysical gamut of a silicon carbide system. But then, maybe if you're more interested in the thermal aspect and losses of a silicon carbide based power system, we've looked at basically making as best accurate measurements of the losses and putting it into a Plex software. And that kind of gives a better understanding of maybe the higher level steady state performance and losses, depending on maybe your switching strategy for your converter and those types of things. So it's certainly kind of a multifaceted tool approach that you might need to take, depending on what it is you're looking to understand from your simulation software.
Gentlemen, thank you for this fruitful discussion. I'm looking forward to the next in 3 months, and we will again extract from the articles in my magazine. And until then, I will take my coffee pot and I will show you the Pennsylvania Railroad. I bought it in the 90s when I worked for Harris, when I came to Pennsylvania to Steamtown up in Scranton. So these are memories, and it's a quarter of a century ago that I got this coffee pot, and it's still alive. So have a good rest of the day, and thank you very much for you attending, and thank you for the audience making it to such a fruitful discussion.